good morning, everyone. It's a pleasure for me to be here. It's my first time at the peer annual meeting. And as Chris said, I'm going to give you a little bit of overview of what is about this project. You may get a little bit annoyed because probably it's one of the few is not talking about earthquakes, so apologies for that, but we'll try to make it interesting. I actually have to confess that I submitted the proposal in November with my basic knowledge about fracture mechanics that I got from a class that I take from Professor Meyer, Politecnico of Milano, and I say, well, I don't really like this project. And then I got awarded. And I have to be honest, since I started working on this, it's actually quite exciting. So I hope you will get excited by listening to this talk. So the idea is to look at develop a methodology where we'll look at the system, component, and material-based approach. And the purpose is how can we estimate the residual life of bridge decks? Because this is an important problem that Caltrans has to solve. Now, this is the team. So there are familiar faces that you know, Professor Conte, Professor Morrison from UCSD. And then the pillars are the postdoc, Dr. Ernesto Hernandez, who presented in August, and the PhD, Rupesh Sestra. And we had also a visiting PhD from the University of Pavia, Simone Reale. Then, usually I go very long with my talk, so I start with the acknowledgements. And so, first of all, I want to obviously acknowledge Caltrans, and in particular Coleman and Sharon are here in the audience because they've been exceptional. It was my first project, and we have to go through a lot of bureaucracy to set that contract in place. It was more likely 7 months, more than 3 months, but that was quite a good process to learn. And then obviously Pierre, because I always had strong admiration from this institution, especially when I was a PhD and I was reading a lot of reports and I've been facilitating this project, and obviously my University of California, San Diego. So this is pretty much the outline. And we will give you a little bit of a project overview for those of you that attend the August presentation done by Dr. Hernandez. And then I will talk about 3 milestones of the project. We have 7 milestones. I will basically touch base on those 3 ones, which we start doing some work. So we start with the project, brief project overview. So the goal is this was pretty much in the RFP, is to develop a simplified step-by-step methodology which allows to use linear FAM analysis. And with this simplified methodology, the idea is to try to predict the residual fatigue life of reinforced concrete bridge legs. We'll talk about this failure mechanism process, which usually happens in different stages with reinforced concrete bridge decks. But what we propose, we say, hey, ideally, we will build a non-linear high-fidelity model, and we will have a linear elastic model, FAM, and we'll try to identify some key performance indicator, KPIs, which will basically correlate the 2 different models. Okay, it sounds easy, but it's not. And in fact, when we put in the proposal, if you look at the milestone 6, which I feed, and the milestone 7, which is the final outcome, we already thought that there could be 4 potential KPIs, thinking about failure mechanisms like fractural, shear punching, and bond. But in reality, or now going deeper and deeper, you know, as a researcher, you start with the proposal and then you realize that what you propose is actually has side tracks. We actually think that we may not need 4 KPIs. Now, the milestones that we have, we will start from a bridge archetype, and this is actually being achieved, and we'll talk about this. And this I put Italian, you know, soccer, Euro Cup and won, so achievement. We had to celebrate achievements, and we had a big party with my group. And then we have milestone 2, which will be SN curves, led by Michelle Morrison. And then the milestone 3, the idea is to then look at the system. We'll pick up a bridge, and we'll do a monitoring of the bridge. And this will help to pretty much to feed into the milestone 5, where we took the component testing. But we will also have a milestone 4, where we'll try to have do a stochastic analysis in terms of traffic loading, and this will be led by Professor Conte. So basically, by having, when we will do the testing, the component testing, Then we'll start also obviously validating the nonlinear high fidelity model. We'll also have a data set we're already building. I will briefly talk about that. And that will eventually lead into a milestone 6, where we'll have sensitivity analysis, where we'll run nonlinear high fidelity model, the sensitivity analysis for the linear finite element model, and then we will find these KPIs. They will be probably functions. It doesn't mean they will be just numbers, right? And that will feed in the milestone 7. So we started the project slightly late in October 2024, and we had the first advisory board meeting where we actually talk about, refresh the project, and we talk about what are actually the scope. There was a discussion thinking, do we want to have a methodology that covers all the potential bridge typologies, including the pre-stressed concrete box girder? And then the outcome was, let's start simple and just focus on a particular type, which are mainly reinforced concrete cast-in-place decks. So this is the project outline. I think we can skip it because it's not very interesting. And we can talk about the milestone 1, which is actually the first achievement of the project, where we actually deliver a report at the end of the year. And what we did, we basically, through the help of Coleman and Sharon, we went through the Federal Highway Administration database, and what we did, we looked into, class identification, age distribution, we look into the structure type, and then we look at the deck condition of the several bridges in California. And then from this database, we try to come up with bridge architects, family of bridges that will be used for our analysis in the following milestones. So, I mean, for me it's new. When I just came to San Diego less than 2 years ago, I didn't even know how many bridges are in California. So that was a good start, 25,000. And then, going deeper, I mean, you can see that we have majority are reinforced concrete cast-in-place decks, and then you have half of the bridges are all reinforced concrete bridges, and fully reinforced concrete. And then when we look at the construction age, you will see that we have, I think we identified, I will talk a little bit later, the most vulnerable bridges will be in this range. We'll look at mainly at those ones, but we'll say even this is, let's say more vulnerable in terms of high cycle fatigue. And this is pretty much the bridge typology that was at the part of the discussion that we had in the first meeting, where we're basically looking at these multi-girder reinforced concrete bridges. And you will see that what it governs is very important as a parameter is the spacing of the girders and the deck of the thickness of the deck. Now we did just to give you an idea, very simple numbers. If you look here, for example, we start looking at what have been the changes of Caltrans. So the bridges built from 2021, regardless of the girder spacing, they start with a minimum thickness of 8 inches. While the bridges built from 1993, you can go to the minimum of 6.5. Now then, if you will calculate the cracking moment, which is very important to see how that the fatigue failure triggers, we actually found that if you are pretty much if you go beyond the spacing, girder spacing of 9.9, then you pretty much have a cracking moment, which is the ratio between the cracking moment of the deck built in 1993 or earlier and the 2021 is pretty much 1. And it's the same in both directions. So basically it means that if you are in the range below the 9 feet spacing, that means that you have a cracking moment that you can be 60% of the actual design specification. Why this is important? Because I will show you later, this will trigger premature cracking, which are quite important to trigger a sort of beam-like mechanism, which is quite critical for fatigue. So this is the bridge archetypes that we selected. These are the table. And maybe it's better, instead of trying to bother you with the numbers, I show you these. So this is a family, right? So we'll have simply supported single span, then we'll have tree span and more. And the idea here is that these will be the seed models for our analysis. Now, what I want to mention, this is highly simplified. I think one thing would be have to capture from Caltrans is how many of those bridges have a skewness effect, because that will be very critical in terms of especially localized stresses close to the abutment. Okay, so this is milestone 1, and then I now want to give a little bit of overview about milestone 3. Milestone 3 is pretty much the selection of this. We are talking about the system, which bridge we select. So, of course, because we are not putting permanent monitoring, the idea is to have take snapshots in different conditions. So, with the help of Coleman, we basically try to select bridges close to UCSD, to San Diego. And as you can see, we're being very clever. We pick up the one is furthest away from UCSD. So, but it was really the best one, and I will tell you why. And so the idea is that here we now want to understand with this system the loads. We want to understand the loads, right? The criticality of the loads, the traffic loads, but then also identify the critical hot spots in that bridge because it's a multi-girder. And then potentially with the high-level instrumentation that we haven't. We start doing literature review on that, on the instrumentation. We'll try to have an understanding of what are the stress levels in the different hotspots that we identify. Now, this is actually the fun part, selecting the bridge, because we also had, actually went to see those bridges. These were the 6 bridges, and then what we can say is that in terms of selection, we want to have one which is close to these archetypes, right? Because then it could be quite valuable for our research program. Accessibility to the deck, underneath, and maybe even at the top. And then quite important is the traffic stations. So we have the vehicle traffic station, the WIM, and then the commercial stations, right? These are for the big trucks. So this was the criteria, and then we came up with 2 bridges, and that we selected out of the 6. And then out of those 6, then we went to, those 2 bridges went to do the sightseeing. That was really exciting, because after 2 years being in the office, that was my first time going on action with all the team. And what at the end we selected the second one. This one was interesting because it was widened, and you have old and new, so in the same bridge, but has only an access on one abutment, and because they have the river, the other side was not accessible, so it had a lot of limitations. And then our choice was to go with this one because it's a twin bridge, so you have traffic load in both in the opposite directions. And then what we like is that it's accessible on all the sides of the spans, right? We will put instrumentation only on the side spans because we're not allowed to put instrumentation in the middle span because there is a road underneath. This is not allowed by Caltrans. And so the other key with this one is that we could put a camera and detecting the load coming from the top and then correlate with the underneath, with the measurement instrumentation we put underneath. So there's quite value from this. And obviously you see there are already signs of crack on one side and this side. Then of course I said, okay, there is crack here, there should be crack here. But when we went to see that bridge, there was nothing. So this tells you how uncertain and how many variables you have to consider. And then, as I mentioned before, we checked this bridge in terms of stations. We have that, both the stations are not far away, 30 miles. So I know there are exits. We will not give you the exact traffic model, but we'll have a qualitative understanding what will be, the loading going on that bridge. Okay, now I have 3 minutes to talk about the milestone 5. So the milestone 5 is basically start developing understanding in order to prepare the test setup of the component, right? And what you can see is this, that if we think about what is the damage propagation happens with these bridge decks, you have a vehicle loading going here, you have cracks propagating transversally, and then they get bigger, and then you will have a beam-like behavior happening like this. And you will have, potentially, if you keep loading, it will be compression failure of the strut. So you will have micro-cracking developing within the struts. And then because you lose stiffness, you will go back and have a redistribution on the other direction, and will have a more punching type failure. So now, this is the strain profile. Now, there's been a lot of work on pulsating loads, and we want to go away from that. So we basically, what we start doing now, we start collecting a lot of data on testing done on moving load only. You can see there is a total different pattern. This is the strain profile. But what is important here, this is a quite good work done by Coelho, Stephen. Actually, this was a work commissioned by Caltrans, looking at the metacrylate rehabilitation, resin to put in the cracks. And you can see that the pattern is totally different, because if you start with the pulsating, you basically induce, already since the beginning, that type of punching failure, which is not representative of what happens in reality. And so, you know, then we were thinking and losing. Then I put these that I used to do as a student, the Pucher charts, the influence surfaces. And what I want to highlight is that this is typical, is an influence surface of the moment at mid-span in the longitudinal direction where you have the loading. And so what you can see is negative here, right? If you have a loading here and here, means that the moment gets negative. When the load moves here, the moments get positive. This is actually even bad, because it means that you will have alternations of sign of stresses in the longitudinal direction. And so what we did, because of course we will use the system testing, the monitoring will give us a lot of information, but at the same time, what we want to do, also have information from the testing from a moving load. And so we went through extensive literature, and Dr. Hernandez has been amazing, because he collected more than 100 Japanese papers written in Japanese. We translated, and then we turned it into a data set where basically the Japanese, as you can see in this slide, they started actually doing a lot of testing on moving load since the 80s. And so, and there is a very famous Matsui analytical model proposed for a beam-like failure type, as you can see here. But then what we did, then we basically collected, we have now 73 moving load. We are talking about moving loads testing. And the idea is to use these, you know, combined with the system testing to feed, you know, information, our information for the component testing. So what means that we will have to look, you know, we will have to understand how, you know, we have normalized stresses in the beam-like failure, thickness, and then we also the reinforcement ratio in the longitudinal transversal, how those parameters will actually affect our decision-making process for the component testing. And we will also try to see where actually Caltrans, you know, geometry and mechanical properties fit with the Japanese data set. And so this brings to the conclusion where basically, I have to say, the more I present, the more I get excited about this project, because you know, you learn something totally new. But I think we got the milestone, and we'll have to do further refinements. In the milestone 3, now we have to think about instrumentation. I know here there are top experts, you know, in this field, and we start thinking about that. Of course, we have a limited budget, so we are open to offers from research community to offer in-kind contribution. That will be very, very appreciated. But the idea is not, we don't want to overkill, right, with the high refined instrumentation, because we are also for the testing, the component testing, what we are trying to do, we are also using the data set, the very valuable data set we are building from moving load. Now, the last thing I want to mention, we don't have a rolling, we don't have a moving load in the UCSD, and we don't have funding to do that, right? Unless countries want to invest on that, that could be an option to discuss. So what we do, we will think about pulsating actuators, and we'll try to reproduce that strain profile along the concrete deck. That is the idea. But remember, we may also to start thinking that this will not be enough. We will also have to think about having not just two these And then the third one, I start thinking, what will be the effect if you load on one side? What will be the effect on the other bridge tank? So a lot of things going on. So I hope to see you next year, and I will have more information in the next chapter of the story. Thank you very much.